Okay, we're going to go ahead and get started. My name is TJ Willits with Veolia Water Technologies, and I want to welcome you to today's anaerobic presentation for continuing education. And this webinar is entitled Preparing for the Future. Some technical things to go over before we hop into the main part of the presentation. Obviously, you should be hearing me speak now. If you have issues with your audio, if you're listening over your computer speakers and there's some issues, you could go ahead and switch over to the phone call option, and then you could get and log in via your mobile telephone and listen through there if you have any issues with your audio. If you haven't noticed, your microphone is already muted. However, you could go ahead and put your questions in on the right-hand side. There's a questions panel over there. Go ahead and type them in throughout the presentation. We have some time reserved for the end of the presentation to get through as many questions as we possibly can. So go ahead and do that. Just one thing to make note of here. If you're relatively new to these webinars as a part of the series, we just want to let you know that after the webinars are conducted, we go ahead and post those webinars on our website. So if you log on to veoliawatertech.com and go to our upcoming webinars page, you can see a list of some of the other webinars that we have there, and you can go ahead and log on and watch those at your own pace on demand. So feel free to do that if you want to get caught up to watch some of those webinars. And of course, if you attend this webinar, you'll receive a PDF participation certificate, and it'll be emailed automatically 1 or 2 days right after event. I know that sometimes at some facilities there might be a few people watching within the same room. If that's the case, just in the comments within the survey, go ahead and enter in who might be watching with you, and we'll make sure that we provide a participation certificate to anyone else who might need one. Okay, we're going to transition to the main part of our presentation. We have 2 expert panelists here that we're fortunate to have to share their experience with wastewater treatment for industrial facilities. The first presenter that you'll hear from today is Rob Franken. Rob has more than 32 years of experience in the development and commercialization in water treatment technologies. At his current role at Veolia, he is the lead in the commercialization efforts for Veolia's extensive biological wastewater treatment technology portfolio, which includes anaerobic, aerobic, and everything in between. Also with us today is Mr. Greg Rosenberger. He's the Vice President of Light Industries at Veolia Water Technologies, and he manages all aspects of bringing projects to customers and making sure that there's a clean execution of those projects so they commission and work properly for them. So at this time, I'd like to hand the webinar over to our first speaker, Mr. Rob Franken. Rob, are you here?
I'm here, TJ. Thanks for that introduction. Hello, everyone. I'll jump right into it. This slide gives you an overview of what we want to talk about today. Basically, how to get ready for the future. All of you have an anaerobic treatment plant on your site. And we're going to dive in today into the different scenarios that could drive or trigger upgrades or modifications to your plant to deal with new situations. And we're going to sketch those scenarios for you. So, as I said, anaerobic treatment is a kind of a central theme because that's the invite has been sent out to all of our anaerobic treatment plant operators. So the question is, what shall you do with this plant in order to make it like future-proof, depending on all the different scenarios that you could be facing in the future? So let's look at those potential scenarios. The first one is anaerobic treatment usually is a pre-treatment step. So many of the owners send their wastewater to a sewer, to a POTW. Now, obviously, always always faced with surcharges, sometimes risks of NOV, certainly when you are close to your capacity or in overloading situations. So that is definitely a scenario in which case you would be looking at a planned upgrade. If your production, and we're seeing a lot of that right now as we speak in the United States, where a lot of the food and beverage industries in particular, but also some of the paper mills are expanding This obviously has a big impact on wastewater discharge, and this will typically require update of treatment plans as well. Sometimes those permits change either to the sewer, or if you are a direct discharger, permits get updated, get more tight. So in order to make your plant future-proof, you have to consider what's coming and be ready for it when it comes. So that is definitely also a driver. And the last but not least is many of our clients have CSR objectives, corporate social responsibility objectives. For instance, reduce carbon footprint. What can I do with my wastewater treatment plant to make it more environmentally sustainable? Should I be talking about water reuse? All of that sort of scenarios could trigger thinking about what I shall do to make my plant future-proof. Now you can categorize the different topics, the different treatment technologies into those 4 globes that we show here. On the top one is quite obvious. If you have a capacity need on BOD and COD removal, that is obviously something that is quite straightforward. If you have capacity expansion in your production, then COD, BOD removal on top of what you already have there for anaerobic treatment is something to consider. Can also be as a post-treatment to the existing plant. We will talk a little bit more about that. Anaerobic treatment doesn't like TSS and FOG typically, especially if you talk about high-rate anaerobic treatment. So sometimes you can consider to do a deeper pre-treatment prior to the anaerobic treatment in order to just shave load off the wastewater before it enters into your biological system, or just make the operation more steady, more stable. So there's a variety of technologies that we have there that can be considered. On the left side is nutrient removal. Anaerobic treatment only really removes COD and BOD and does very little to nutrients. Sometimes we even have to add nitrogen and phosphorus, which could give some issues downstream. So if there are requirements, I mean, with direct discharge, there are always requirements, and sometimes also for sewer discharge, for nutrient removal, then there is a whole range of technologies to do that. The last one is pathogen removal, basically only required if you are looking at the direct discharge. If you have to meet a certain E. coli limit, then we can look at different disinfection methods to tackle that issue. So zoom in a little bit deeper, TSS FOG removal. I already mentioned anaerobic treatment, especially high-rate anaerobic treatment, doesn't like TSS and FOG. Many of our treatment plants have pre-treatment to do that. I mean, you can think about classical clarifiers to settle out solids. When you have FOGs in many food industries, we have that, like dairies, etc. Then typically that is floated out in a kind of a DUF, with a DUF technology assisted with chemistry. So that obviously produces a primary sludge that no one likes to have. So if you can prevent it, I guess you should. But it is definitely a way to make a high-rate anaerobic treatment work more smooth. TSS removal can also be considered at the back end of the plant that you have. If everything is well, but you're exceeding a TSS limit, for instance, when you have a POTW permit level that you need to meet, then you can consider to bolt on TSS removal capacity. That can be a DAF unit, it can be a filter system, it can be a high rate or low rate clarification. So there's several different types of options there. And I mean, you can go as deep as 10 ppm of TSS. So typically these technologies work very well. The next one shows the options for BOD and COD removal. If you have an anaerobic treatment there, yeah, I mean, it all depends on the situation. You could consider just to expand that anaerobic capacity. That is often done in case, I mean, if a production site expands with different production lines, then this is an option to do. If it is a requirement that cannot be met with anaerobic treatment, then you could look at aerobic treatment, obviously, as a method of post-treatment. Depending on the requirements, if it goes to a POTW, you don't typically need such a deep removal of BOD, COD. If you go to a direct discharge, obviously you have to meet much stricter limits. But with an aerobic post-treatment system, you can typically reach BODs of 10. A favorite technology that we have is MBBR, but we have many other technologies, and we'll talk a little bit more about that. Nutrient removal is a little bit more complicated and getting more and more important. I think we're seeing that the limits, the NPDES limits are getting tighter and tighter, certainly in certain states. And of course, if you have anaerobic treatment, it doesn't do much. It doesn't do much to nutrient removal. In particular, of course, we're looking at nitrogen and phosphorus, and we can also see that many of those limits are actually pushed to the industrial clients. So we are also seeing more and more that we're asked to look at nutrient removal technology for on-site for industrial clients. There's several ways to do this. Nutrient removal, you're really talking about nitrogen and phosphorus. Now, nitrogen is typically removed biologically. I mean, it depends on the limits. Ammonia is always, there's always a limit for ammonia, but there's not always a limit for Kjeldal nitrogen. So if that's the situation, we can just nitrify in a biological system, and ammonia will be nitrified and give nitrate, and we'll show a few cases of that in the case study. If it's phosphorus, then you typically look at chemical precipitation of phosphorus. You can also do it in a biological method, but I think in the US in particular, still today, chemical methods are more usually applied. And that is then in combination with some sort of filtration and supported by flocculation and coagulation with chemistry. Pathogen removal, I will be brief on that. I mean, this is typical, like with UV. We typically do that with UV in open channels where you have a UV light, where the final effluent, which at that point has to be really clean, otherwise this will not work. Where you, with a certain residence time, you expose the water to UV light, and that will reduce E. coli to the limits that are typically required. So with that, I think I give the floor to Greg, who will zoom in a little bit on those different technologies.
Thank you, Rob. This is Greg Rosenberger, and I'm going to go over a couple of the technologies that Rob talked about in a little bit more detail, and then we're going to look at some case studies of facilities. So when we're talking about probably the most common post-treatment after anaerobic, which is aerobic treatment, essentially, as most of you out there who have anaerobic systems know, you probably get 80–90% BOD, soluble COD removal. But sometimes the sewer limit might come back and say they need lower numbers. Maybe you have to get under some type of 200 or 300 ppm value, or your sewer surcharges are going extremely up, or if you get under a certain value, you only pay on flow and not COD load. So when it comes to BOD COD removal, typically we look at MBBR technology. MBBR stands for Moving Bed Biofilm Reactor. And essentially what it is an aerobic system where the biology lies on the media, which you can see there is those plastic chips that look like honeycomb cereal. You load them into the aerobic reactor, and essentially they are there to allow a home for the biomass to grow on. We can use these for both BOD and COD removal, and for nitrogen or ammonia removal as well. They work very well after anaerobic systems. They have small footprints, and they're extremely easy to operate as well. Next slide. An MBBR system inside, if anybody's ever wondered what an MBBR system looks like inside a tank, or in general aerobic systems, you have air that needs to be blown in. So obviously you have drop pipes that come down from the side of the tank. You have a big diffuser grid at the bottom of the floor. The nice thing about MBBR technology is the diffuser grid is stainless steel pipes with drilled holes in them. So you don't need fine bubble diffusers or membrane diffusers that eventually have a maintenance cycle on them that you have to take offline. These are just stainless steel pipes with holes. So pretty much you don't really have any long-term maintenance. You don't have to take the system down ever, which is one of the huge advantages of MBBR. Tanking, you can build that mostly in the industrial world. We like to build out of steel, so bolted coated carbon steel tanks. But it can be a concrete tank. You can even retrofit some existing tankage if you have it available. And then really the big unique thing about an MBBR is you see those sieves there. Obviously, you want to keep the media in the tank. So you need a sieve on the inlet and outlet piping. So essentially, the media just doesn't flow out with the regular water flow. The key to the technology is the media. And that is where the biomass lies. The picture on the left there is virgin media, as it is sort of when it comes from the factory. And then the picture on the right is a carrier with biofilm on it. All the brown you see is actually the biomass that is on the media itself. That's what's reducing all of the BOD and COD, or is reducing the ammonia in the system. It all grows on the media itself. Besides just BOD and COD removal, you can also do nitrogen removal with MBBR reactors. You can nitrify, which means if you have an ammonia limit, you basically blow air into the tank and oxidizing bacteria take the ammonia to nitrate. So if you have an ammonia limit, you can get the ammonia down to almost negligible values. Some people, as Rob said, have a total nitrogen or TKN limit, which means you actually have to eliminate nitrogen. You just can't nitrify it. And in that sense, you need an additional step where you convert that nitrate to actually nitrogen gas, and it just goes out into the atmosphere. So there's two different types of nitrogen removal, and you always have to be understanding of what that is. Do you have an ammonia limit, in which case it's a pretty simple system. It's just a reactor with that blows air into it and you nitrify, or do you have a TKN or a total nitrogen limit, in which case you need an additional reactor vessel, levels of recycle. It's a more complicated system if you actually have to remove the nitrogen from the system. We do a lot of retrofitting of systems as well, where you can put in media before an existing aerobic plant. That's called IFAS system. Another thing that you might hear about out there, it's becoming a little bit more popular, is biological phosphorus removal. So there's typical two ways to get rid of phosphorus. You either precipitate it out with a ferric or an alum, and it turns into a chemical phosphorus sludge, or you have a specialized biological system design where the biology actually uptakes the phosphorus. So instead of the phosphorus becoming soluble and need to be taken out later with chemistry, you use unique operating conditions in the aerobic system so that the phosphorus gets taken up within the biomass itself. So all the phosphorus comes out with the waste biological sludge. So it is something that is out there, and for certain wastewaters, it can be an economical system to put in. Recognize that you pay a little bit more upfront on the capital side because you need a little bit bigger tanks, a little bit more sophisticated equipment. But long-term operating costs, you don't require anywhere near as much chemistry, or maybe no chemistry at all. So one of the big things about phosphorus too is what is the level of phosphorus that you need to get to? There's limits out there. I've seen limits. Some people have no limits on phosphorus, but a lot of places are starting to put phosphorus limits in. We've seen phosphorus limits less than 10, less than 5, less than 2, less than 1. And what this graph is trying to show is that on the y-axis is the amount of iron you have to dose to remove phosphorus. And on the x-axis on the bottom is actually the concentration of phosphorus in the effluent. So as you can see, you know, when you're at 10, when you're at 1, when you almost get down to 0.5, the ratio of adding iron to phosphorus is pretty linear. But once you have to go below 0.5 ppm of phosphorus, you have to start adding incremental ferric chloride to get it out. So you start adding a lot of chemistry. And if you have to get down into that 0.2 or 0.1 range, you start adding huge amounts of chemistry. So always something to keep in mind if you have any influence over your phosphorus limits. Ideally, you don't want to have to go much lower than 1 ppm. 0.5 ppm is something that's doable. Once you start getting less than 0.5 ppm, that starts to get really low. You start having to add a lot of extra chemistry to get there. Detection methodology starts to become a little bit of an issue. Any type of leak by that you might have becomes an issue. So it's just something to think about, that if you sometimes have some influence on your limits as you're talking to the municipality or you're talking to the local DEP, try to keep that phosphorus limit if you can around that 1 ppm range. Another technology used to remove phosphorus, and it can remove TSS as well, but mainly phosphorus, is the active flow high rate clarifiers. And what these are really good for is when you have to remove a lot of phosphorus. So if you only have to remove, you know, if you're coming out of your anaerobic or aerobic system, let's say you have a phosphorus that's 5 or 6 or 7, and you need to get it down to 1. A lot of times you can do that with your conventional technologies. You can add a little bit of ferric or alum, maybe before your DAF or into your clarifier, into a disc filter, and make it work. But what happens if your phosphorus is 50 or 100, 150, and you have to get it down to extremely low levels? In that case, sometimes it's not really good to do that all in one step or with one specific piece of equipment. And that's where the active flow technology shines. It's a package system. It's a high rate clarifier. It uses micro sand as a ballast. And it's built to be able to take phosphorus from 100, 150 down to low single digits very effectively in a very compact system. So this is what a high rate active flow looks like. It basically has some chambers, some coagulation and flocculation chambers before the clarifier itself. So you add chemistry typically, obviously, usually some type of coagulant, ferric or alum, that actually binds up that phosphorus, potentially some polymer. And then it goes into the clarifier step, which is a lamella separator type step. And this is all packaged in a shop fabricated piece of equipment. So it's extremely compact compared to if you just did this with gravity clarification per se. Another technology out there that you'll see a lot is disc filtration or drum filtration, microfiltration. And that's a lot of times for TSS removal. When you go to direct stream discharge, if you're looking to go to that low of level, or maybe even go to some water reuse, putting back to a cooling tower, or some of the dirtier applications for water reuse. And you need typically TSS levels down to like less than 10 ppm. This is the type of technology that's used. You put this after your primary clarifier typically. So you might have a DAF, or you might have a gravity clarifier after an aerobic system. And then this will take that, you know, maybe that clarifier, you get 30 or 40 or 50 ppm of TSS, and you need to take it down to less than 10. This is a technology that is the standard in the industry to get down to those very low TSS levels. And in addition, if you need to clean out a little bit of phosphorus, this is also a good piece of equipment to do that. You can add chemistry in a coagulation and flocculation tank before it, and then this filter will remove that chemical phosphorus sludge as well. So as I said, there's a typical, you'll see this after primary clarifiers. There's disc filters and drum filters. They're actually the same technology. It's just, basically drum filters usually take a little bit smaller flow. Disc filters are for larger flows, but same technology, same cloths and everything. And a lot of times in the municipal world, they typically put this right after the primary clarifier, and they don't really need much chemistry. In the industrial world, we found that typically you need chemistry to get down to very low TSS levels. So typically you have a coagulation and flocculation step before the filter. So now we're going to go over a couple of facilities that sort of show where these different processes come into play here. So the first one is a flavorings company, and they have nitrogen and phosphorus limits. So there was an anaerobic reactor, and then to get rid of the ammonia, there's an MBBR. And typically when you do MBBRs and you need to get rid of ammonia, you do it in 2 steps. So the first tank is called a C stage, or your carbon stage, or a COD removal stage. And out of that stage, your BOD or COD will be extremely low. So then the second stage is where it converts the ammonia to nitrate. So that allows that second stage to be highly specialized bacteria, specifically for oxidizing ammonia. And then it goes through a drum filter to remove both the TSS and to remove some phosphorus limits. So this facility had low BOD, low TSS, low ammonia, and low phosphorus limits that they needed to meet. So it used the MBBR for ammonia removal and the filter for TSS and P removal. So you can see here that the ammonia levels can be pretty high, 200, 300, 400. And typically, the ammonia coming out is less than 1 ppm. So you can get very low ammonia coming out of an MBBR system. So I'll change this next one over to Rob.
Yeah, thanks, Greg. So this is another case. This is a project in Pennsylvania for a confectionery producer. This is a system which is designed to meet discharge limit criteria. You can see that in the right bottom corner, BODs of 10, TSS 10, ammonia 5, phosphorus 2, and a pH limit there. So this is obviously a very high COD wastewater, a pretty sizable project of 35,000 pounds per day of COD. So this is such a nice project for us because it sort of bundles all these different technologies that we discussed throughout this presentation together. You can see that the wastewater is collected and first screened, typically 1 millimeter screen to collect the water in an equalization tank. Equalization tank, all of you are anaerobic treatment plant operators know that equalization is important. So there's a standard UASB system here that will sort of remove 85–90% of soluble COD. All the carbon goes out. That obviously gets converted to biogas, and in this case, there's also a CHP unit here to recover the energy from that gas. Now, as we said throughout this presentation, you only remove COD, BOD there, and that is obviously in the anaerobic stage not good enough. So post-treatment is required. As Greg explained, in this case, we're using a 2-stage MBBR system, with the first one removing any residual BOD, COD, and then the second one specifically designed for nitrification of any of the ammonia that's coming out of the UASB. All the solids that are generated in that aerobic process has to be removed. We do that with a DAF unit, dissolved air flotation unit. But because of the tight limit in the effluent, there is further treatment is required. So in this case, we use that Hydrotech disc filter process, which is also in this case supported with chemistry in order to meet that phosphorus limit of 2 ppm. And when the water comes out of there, it is pretty clean. And as I said, this water is this plant is designed for meeting actually surface water discharge limits. So we also have a disinfection system at the back end just to meet all those criteria. On the next slide, you have this slide shows how the ammonia reacts in the system. So in the anaerobic environment, all nitrogen-containing compounds will basically be converted to ammonia, which obviously shall be removed, and that we use that nitrification process for that. So in this case, you can see ammonia is typically in the 10 to 25-ish range coming out of the anaerobic effluent, and after the final MBBR nitrification stage, it reaches less than 1 typically ppm of ammonia. So that MBBR process works very well for that type of application. The phosphorus in this plant, as I said, we're using at the back end the filter system for phosphorus removal. There is a flocculation and coagulation step. We're adding iron to the system to precipitate out that phosphorus as a solid, and then the filter system is able to catch those solids. So typically here, like 10 ppm of phosphorus coming out of the aerobic system, and that has to be removed, and you get down below to like 1-2 ppm typically. That's what it's designed for. The next slide shows the active flow system that Greg mentioned. So in this case, we're using this active flow high rate clarification system to remove solids and phosphorus out of an activated sludge system. It's actually quite a special application. So you can see that the raw water, which is basically the activated sludge mixed liquor, has very high suspended solids level, like 6 grams per liter, the left column. And with the active flow system, you get to below like 20 ppm. That's what you see on the clarified water TSS column. And in this system, you can also at the same time remove phosphorus. So you can see the phosphorus is really very high. This is a kind of a dairy application where you have typically like 180 ppm of phosphorus in that aerobic effluent, and you can get it down to less than 1 in this one stage active flow high rate clarifier. Obviously, I mean, we have a chemistry there to support that. The next slide shows a last case where we are using that Hydrotech filter system for the removal of nitrogen. So you can see phosphorus, yeah. Sorry, yeah, phosphorus, yeah. So you can see on the pictures how that phosphorus flocculates after you add the metal. It flocculates quite nicely, and then you can actually separate it out on that cloth filter that you see at the bottom picture. So typically here, I mean, you get this very low P levels that we can meet here. If you see those right-hand columns, that is less than 0.5. But as Greg explained, the other column shows the molar ratio of metal that you have to dose per mole of P, and that is really in a very high ratio that you have to do there. It's like, I mean, I'm looking at it now, 20, 25, 30 molar ratio of iron in proportion to P. So that is comes, of course, at a cost, but it works very well, and this technology is very suited for that. So I think that is the last case that we wanted to present. So on the next slide, I sort of want to wrap it up. We have a kind of a checklist. So, I mean, the whole objective of this presentation was to give you a little bit of an overview of what you can do in order to make the plant future-proof, depending on the issues that there are in terms of permit, in terms of capacity, in terms of operation, in terms of cost. And so this is the kind of a checklist that you can go through and see what you can or should do. So I mean, the top one, obviously, cost is always the biggest driver for any action, I would almost say. So if you have high surcharges, high operating costs, then it's certainly something to consider upgrading the facility to see if you can do things in a more clever way. Sometimes there's a risk of NOVs, notice of violations, compliance issues. I mean, that will always trigger management. If something like that happens, then everyone wakes up and, okay, what do we need to do? And then everything has to move fast. So it's always better to anticipate there and not get into that kind of situation. So if you want to be future-proof, you also need to have a little bit of a vision about what is that compliance requirement going to be in the future. What are the, and that's the third bullet there, what are the permits going to be when my current permit expires? I mean, whether it be an NPDES permit or a sewer permit for the POTW. And how is that going to affect my operation? Then we talked about the need for capacity expansion. If you have BOD, COD, just more of it coming out of the factory because of new production lines. I mean, that should be known in advance well enough. Now, that is not our experience. That is wastewater treatment is usually the last thing that people think about when they are expanding the factory. So, but nevertheless, it is important to consider that at an earliest possible stage so that you can anticipate and rather than firefighting when that extra load is coming. Then there's some few other considerations. Land costs a lot of money, so you always try to limit footprint. Is there space for expansion? If not, then what do you do? What do you do with your current infrastructure? There's always a need to make maximum use of existing assets. How do you integrate that into a new system? How do you repurpose some of your plant? And how do you, for instance, an obsolete tank, how to convert it into an MBBR system, for instance, and see how you can most cost effectively accomplish upgrades that will make your plant future proof. And then the last bullet here is, I mean, if you have struggling to operate the plant smoothly because of stability issues, I mean, is there anything you can do in terms of monitoring and control that you can do, that you can bolt onto a plant just to make the operation easier? I mean, how it can easier be maintained, how it can be easier operated. So, I mean, obviously, as Veolia, we have all the technologies in-house to help you and assist you with all these sorts of issues. What we also often do, and maybe we're not as well known for that, but we assist our clients with like engineering or feasibility studies to assist the client and go over his scenarios. So what is your treatment requirement in 2 or 3 years? What is your current situation? What is your current asset? And then based on that whole overview, we can actually develop different scenarios. And what are the cost implications of each scenario in terms of CAPEX, in terms of operating cost? And that is a useful tool for our clients to guide them in decision making, in planning CAPEX requirements, and get really a grip on how much space is required, what can I do with my assets. So that is a really helpful tool that we're also able to offer. And I think with that, I want to wrap it up. I think this is sort of the overview that we wanted to present. So back to you, TJ.
Great, thanks Rob, thanks Greg for that. There's no such thing as a crystal ball when it comes to wastewater, but hopefully some of those areas and tips and planning ideas might open some ideas and discussion with different people at your facilities to start thinking about these things and mitigate as much risk as possible. So we really appreciate that. So we're now going to enter into our question and answer portion of our presentation here. We have about one question right now in queue. So feel free to go into the right-hand side of your screen. And if you have a question about anything that you heard today or anything related to biological wastewater treatment, go ahead and enter it into that question panel, and we'll do our best to answer it and get to as many as possible. So one question we have here is, you discussed the cost of chemical costs compared to when using physical chemistries to remove P, but how have you looked at it compared to managing sludge costs between whether it's more of a biological removal of P versus a physical chemical removal of phosphorus? Is that something that you've looked at, Greg or Rob?
This is Greg. I mean, there's no doubt that if you can do P removal that is going to have lower sludge takeaway or haul costs, because in the end, the phosphorus sort of just gets assimilated into the aerobic bacteria, and realistically speaking, you don't really have any extra costs because you're going to get rid of that waste sludge anyway. So you almost get some P removal for free with respect to operational costs. I mean, it's a little bit more difficult to operate and has got a couple more steps, but there's no real extra cost because the P just goes along for the ride, you could say, with the bacteria. And the physical chemical, that's all incremental sludge, right? You're going to add ferric or alum. You're going to make iron phosphate or aluminum phosphate, which is a sludge that then it's just additive to what you already have. So that's why some people like to look at BioP. Most of the times when you're looking at BioP, it's more of a greenfield site. That's not something typically you're going to try to retrofit in, where let's say you already have a wastewater treatment plant and your phosphorus limit, you just got one, or let's just say you got one that went from 10 down to 2. Then it's typically where you're looking at the chemical, addition. So BioP we find more when you're talking about more greenfield plants. You have a blank sheet of paper versus sort of utilizing existing assets or just doing something down and dirty. I mean, the capex for chemical P removal is much lower than for BioP. So some people just choose that because of that reason, just lower capex.
We have a question here. It says, so is it wise to add ferric chloride to drive down the phosphorus? They go on to say, this has been our response when we see our P levels climb. Should we be doing anything else?
We would need to know a little bit more about your specific system. So if you want to follow up with an email, we can call you back. I mean, the key in how much chemical you add. I mean, ideally you want to add the stoichiometrically least amount of chemistry to get that P out. So if you don't have good proper mixing beforehand, you're not getting good contact between the iron and the P. You might be overdosing ferric, which is obviously just throwing money literally down the drain. There are, if you really want to get fancy, you can put some more advanced instrumentation on. Are you pacing your chemistry to the flow? Are you pacing your chemistry to maybe some TSS values? There is online P measurements. It's not cheap, but it might be worthwhile. So there are ways to look at optimizing that chemical addition to get rid of the P if you have a hefty bill for chemical for P removal. So you have a hefty bill, there are ways to potentially optimize that.
Okay, and to the person that asked, feel free to follow up, or in fact, we'll just follow up with you and shoot you an email after the presentation and see if there's something more that we can help you with there. Another question is when you see high levels of ammonia after an anaerobic system, what are the main causes for those higher levels of ammonia?
Rob, you want to take that?
Yeah. So I mean, it's just the biology that is going on in the anaerobic system. If you have like proteins in your wastewater that contain obviously nitrogen, the proteins get degraded, and it's just a degradation product of the COD that is being converted in the anaerobic process. So that is where the bulk of ammonia typically comes from. That's why we see ammonia issues often in like food industries where there's a lot of proteins. Sometimes it can have a more like a chemical source, but that is very much dependent on the type of industry. So in general, I think you can say it's the degradation product in the anaerobic process. In some cases, it's actually the ammonia that we're adding as a nutrient to the anaerobic process. We've also seen situations where we have to add nitrogen as a nutrient, but then there's always some overshoot of that, and then you have to actually remove that if you have strict limits, and then you have to remove that in the aerobic post-treatment system. So that is another source of ammonia that you might have to remove in the post-treatment.
Okay, well, at this time, we don't have any additional questions in the queue right now. So it looks like we're going to go ahead and complete this webinar. If anyone does have any questions that maybe you didn't want to ask on today's broadcast and want a more personalized response, feel free to shoot myself an email. My contact is on the screen, and I'll connect you with one of our engineers to follow up with you. So with that being said, I want to first thank both of our presenters today, our panelists, Greg Rosenberger and Rob Franken, for taking the time to work on this presentation and share their experiences with all of us here on the call. And also want to thank all of the people here that took just about an hour out of their day to go ahead and continue their education and be better operators and managers of their wastewater treatment system. So be on the lookout. This is our second quarter anaerobic operators webinar in our series. We're going to have one after summer, so fall or early fall. Really glad to have you here and a part of this community. And if there's anything that we could do to support you, again, please don't hesitate to get in contact with us. Thank you all and have a great day.